This video is designed to give an overview of some wave vocabulary and properties that we will apply in our study of mechanical waves and sound. We are going to start with our definition of a wave. A wave is a vibration or disturbance in space that transfers or carries energy from one place to another. So anything that can transmit energy through space is going to be considered a wave for the purpose of our study of waves and sound. Now, a medium is something that some waves use in order to transmit that energy. So it's the substance or physical environment through which a wave will propagate or travel upon. And so some examples of mediums would be things like the air or water or even the earth during an earthquake. Now this is where we can get into mechanical waves, which is what we'll be studying in this course, which are waves that require a medium, such as sound, ocean waves, earthquakes, those ones previously mentioned. But there are also electromagnetic waves, or EM waves, that you maybe learned about in chemistry class when you learned about the electromagnetic spectrum, like visible light, infrared rays, gamma rays, X-rays. Those all fall into the electromagnetic waves, or the electromagnetic spectrum. And these types of waves do not require a medium and can travel through a vacuum. So for the purpose of our course, know that both kinds of waves exist, but the focus in AP1 is on mechanical waves, ones that require a medium. So we're going to further classify waves. So we're going to be dealing with mechanical waves. And those mechanical waves can travel in two waves on the medium. The first way that it can travel is a longitudinal wave. That's when you have a fixed point that moves parallel with the wave motion. As you can see from the motion shown here, the dots are showing that the particles of the medium are moving left and right as the wave travels left and right. So this is an example of a longitudinal wave. Now we define the area where there's high density and pressure, where those molecules move together at first as the wave travels or propagates. We call those areas compressions. So when the molecules are close together, when things are very dense, we call that a compression. We then call the space where those molecules are more stretched out rarefactions, and those are areas of low molecular density and pressure. And so in order to have one wavelength, we would go from one area of compression, have a rarefaction, back to an area of compression, so that would be considered a wavelength. You could also do from like end of the compression, so the rarefaction to the compression back to where it started. So again, one wavelength means it goes through the whole cycle. So there's a compression and a rarefaction in one cycle for a longitudinal wave. Real-world examples of longitudinal waves would be sound, as you can see here. You can see the compressions, and then the rarefactions would be where these molecules are further apart, as well as P waves, which is a type of earthquake wave, where the ground would shake back and forth and the wave energy would travel from left to right in this picture across the medium, which would be the ground. Now the other way that a mechanical wave can travel is what we call a transverse wave. And that's when we have a fixed point that moves perpendicular to the wave motion. So the wave may be traveling from left to right, but the medium is going to move perpendicular to that direction of wave travel. So we're going to look at a quick example. So as you can see here, if you watch the red dots, they're moving up and down as the wave travels from left to right across the screen. So that is a transverse wave. The word transverse actually comes from some Latin. The prefix at the beginning, trans, actually means across, and verse or versa was used to represent a line, and so you could literally translate that in Latin as like across a line, and so that's what we're seeing here. Real-world examples of transverse waves include ocean waves, electromagnetic waves, so our radio, micro, infrared, visible, ultraviolet, X-ray, gamma, all of that would count as a electromagnetic wave, and those are all transverse in nature. And then S waves from earthquakes. So we have our direction of our wave would be perpendicular to the way that the earth is moving. You can even have waves at sporting events. We are now going to recap the parts of a wave. So when there is no motion on a medium, we say that it's in equilibrium or in its midline position. Now once we have a wave going, we would call this distance here to the crest or highest point on the wave the amplitude. So again, the amplitude is the distance from equilibrium to that maximum vertical displacement here. In this case, we call that the crest. Now, the amplitude for a wave that's not experiencing what we call damping, anything to restrict that motion of the wave, to reduce that energy, this would be the trough, and it's the lowest point on the wave. Now, in a perfect system, this amplitude to the crest and the amplitude to the trough would be equivalent. However, if there is something like friction reducing the motion, they might not be exactly the same. But in an ideal wave, the amplitude to the crest and the amplitude to the trough would be identical. Now, when you have one cycle of a wave, when it goes all the way up to a crest and all the way down to a trough, that's what we call a wavelength. And so if you recall from our study of simple harmonic motion, we did discuss things like frequency and period, which is going to come up again. So we're going to do a quick recap of those topics. Regardless of whether a wave is traveling as a transverse mechanical wave or a longitudinal mechanical wave, these ideas of period and frequency would apply to both. So the period is what we define as the time it takes for one wave to travel or complete a cycle. So either from equilibrium to a crest, down to a trough, back to equilibrium, that would be one wavelength for a transverse wave, or one compression to a rarefaction, back to a compression for a longitudinal wave. And since it is a time, we're going to measure that in seconds per wave. Now, wave is not a unit of measurement. It's more for us to keep track of that it's a cycle. So you can also just write it in seconds. But for this case, since it's the time for one wave, seconds per wave. And the variable is a capital T. It must be capitalized. Capital T signals that it's a period, the time for just one cycle, where a lowercase t could be any generic time. So that capital T is very important, as we learned back in simple harmonic motion and our circular motion units. Then just to recap, frequency is our number of waves per 1 second. Our units would be waves per second, or the hertz, which we can abbreviate as Hz. And it's our script F for our variable. And then just as a reminder, the period and the frequency, if you look at the units, our units are inverses of each other, and that is because that is the relationship that exists between period and frequency. So 1 over the period would equal your frequency. So if I have, for example, a frequency of 2 waves per 1 second, that means it would take 1/2 a second to travel 1 full wave, because I'm going 2 wave cycles in a second. And see how we have 2 and 1/2. Those are inverses of each other. Just to recap what we have covered in this video, we have defined that waves are the transfer of energy through a medium. A medium is the thing that a wave will propagate or travel upon. That we can have mechanical waves or electromagnetic waves, but mechanical waves need a medium, and that's where we're going to focus our studies. That we have longitudinal waves that move parallel to the medium in the direction of the wave, and we have our transverse waves that move perpendicular to the motion of the wave. And then last but not least, we recapped the parts of a wave, such as amplitude, crest, trough, compression, rarefaction, wavelength, as well as period versus frequency.